Welcome to Coast Learning, your starting point for mastering the fundamentals of networking. From the Pacific to the Pines, all are welcome here. This is the Cisco Networking Academy's Introduction to Networks course. This is the first course in a three-part series designed to give you a strong foundation in how networks operate, how devices communicate, and how data moves through wired and wireless networks. Whether you're preparing for a future in IT, working toward your Cisco Certified Network Associate certification, or simply building your technical skills, this course is where it all begins. You'll gain a solid grasp of core concepts like IP addressing, network protocols, and basic configurations, the essential building blocks for any networking role or certification path. Together, we'll cover the foundational concepts that keep our digital world running, from local networks in homes and offices to the vast global internet that connects billions of devices. We'll explore how networks connect people, devices, and organizations. We'll go over the basic components of a networking infrastructure, such as routers, switches, cables, and wireless systems. We'll see the role protocols play in ensuring reliable communication, and along the way, you'll gain the skills to design, build, and secure simple networks. Networking is at the core of today's connected world, from supporting remote work, to enabling smart cities, to powering the apps and services we use every day. And with these skills, you can help shape the future of technology. Together, we'll explore the essential building blocks of modern networks and prepare for the exciting opportunities ahead. Let's get started with the Cisco Network Academy's Introduction to Networks course. In this video, we review Module 1, Networking Today. We will cover how networks play a vital role in our daily lives, from powering communication to driving global business and innovation. We will also explore the different types of networks, key components, and current trends that are shaping the future of networking. How do networks affect our lives? Networks are everywhere, shaping how we live, work, and connect. They power our phones, support remote learning, help businesses run, and keep our homes smart. Whether we're streaming a show, sharing files, or controlling devices with our voice, networks make it all possible. And today, the world is more connected than ever thanks to networking. Networks are made up of several key components that work together to connect us every day. From the devices we use to the hardware that moves data around, understanding these parts helps us see how communication happens. In every network, devices called hosts or end devices play key roles in communication. A host can act as a client, which requests services like web pages or files, or as a server, which provides those services. Understanding these roles helps us see how communication flows across the network. The client-server model is the most common network setup today. Clients like your laptop or phone ask servers for information or resources. Servers are powerful machines designed to respond quickly and reliably. This model supports many services we use every day, such as streaming videos and accessing cloud applications. In a peer-to-peer network, devices communicate and share resources directly with each other instead of relying on a dedicated server. This approach was once common in small home or office networks for sharing files and printers. While it's less common today, peer-to-peer remains important in specific areas, such as file-sharing applications and blockchain systems, where direct device-to-device communication is essential. End devices are the gadgets we interact with, such as computers, smartphones, printers, and IP phones. These devices are where communication starts and ends. Without them, there'd be no way for users to send or receive data across the network. Between the end devices are intermediary devices, such as routers, switches, firewalls, and access points. These devices are responsible for moving data through the network, directing traffic, and determining the best paths for data to travel. That's where network media comes in, the physical or wireless pathways. This includes copper cables, fiber optic lines that carry data at lightning speeds, and wireless signals like Wi-Fi or cellular. The choice of media affects the speed, distance, and reliability of the network connection. To understand how networks work, it helps to visualize them. In this section, we'll look at how networks are represented in diagrams and go over some key terms that describe network connections. Network topology diagrams are like maps of a network. They show how devices connect and communicate. You'll often hear the terms NIC, port, and interface, and they're often used interchangeably. Here's what they mean. A NIC or network interface card is the hardware inside end devices, such as computers and laptops, that connects them to a network. It provides the interface for sending and receiving data, either over a wired connection or wirelessly. A port typically refers to the physical socket where a cable plugs in, such as an Ethernet port on a computer or switch. An interface can refer to a physical port, like a switch's Ethernet port, or a virtual interface configured in software, such as a WLAN interface. Interfaces are usually assigned IP addresses, enabling network layer communication, whereas physical switch ports by themselves typically are not. In the real world, people often mix up these terms, but it's good to know the difference when working with network topology diagrams. Topology diagrams come in two main types, physical and logical. A physical topology shows the actual layout, where devices are placed and how they're wired together. Network technicians and installers rely on these diagrams to set up equipment, run cables, and troubleshoot hardware issues. A logical topology shows how data flows across the network, no matter where devices physically sit. Network engineers, architects, and security teams use these to design, manage, and secure the network's communication paths. Both types of diagrams give different views of the same network, and both are important for building and supporting reliable, efficient connections. Networks come in all shapes and sizes to meet different needs. Whether it's connecting devices in a single room or linking users across the globe, networks help us share information, communicate, and get things done. Let's talk about the different size classifications for networks. Small home networks connect personal devices like computers, cell phones, smart devices, and gaming consoles within a home. These networks focus on basic connectivity, things like sharing an internet connection, printing, or streaming media. Small home office, or SOHO networks look similar to small home networks at first glance, but are designed for business needs such as secure remote work access, shared file storage, and stronger wireless security. SOHO networks typically offer more reliability and security than a basic home network. Medium to large networks support organizations with multiple departments, buildings, or campuses. These networks need higher security, redundancy, scalability, and centralized network management. Global networks connect users and organizations across countries and continents. The Internet is the best-known example, linking billions of devices worldwide. Two of the most common types of networks are local area networks, LANs, and wide area networks, WANs. LANs connect devices within a small geographic area, like a home, office, or campus. A LAN is usually owned and managed by the organization using it. It provides fast local communication between devices. When that LAN connects to other networks, like the Internet, a service provider comes into play. WANs connect multiple LANs across large distances, between cities, regions, or even countries. WANs always rely on service providers because no single organization owns all the infrastructure needed to cover those distances. So what are the key differences between a LAN and a WAN? LANs connect end devices in a relatively small area, like a home, building, or campus, to provide high-speed connectivity. They are controlled by a single person or organization. WANs connect LANs over large areas. They require service providers to carry the data and generally offer slower speeds compared to LANs. As previously stated, the Internet is the largest and most familiar global network, a massive collection of interconnected networks that lets billions of devices communicate worldwide. No single person, company, or government owns the Internet. Instead, it works because networks and providers all over the world agree to use the same standards and protocols. Another example of a global network is the cellular network, which connects mobile devices around the world. Like the Internet, it depends on cooperation between service providers and shared technologies to deliver seamless communication across regions and countries. Some networks are designed for private use. An intranet is a private network used within an organization. It gives employees secure access to internal tools, resources, and data. Many intranets use web-based portals and applications because they're convenient and familiar, but what defines an intranet is the private, internal access, not the specific technology. An extranet extends part of that private network to trusted partners, customers, or suppliers. Like intranets, extranets often use web technologies, but what makes it an extranet is the controlled, secure sharing of specific resources with authorized external users. Whether we're watching videos, joining Zoom meetings, or syncing files to the cloud, our access to the Internet is at the center of it all. In this section, we'll explore the different ways people and businesses connect, and how everything from voice to video travels across a unified network today. There are many ways to connect to the Internet, and different users have different needs. A small household doesn't need the same bandwidth as a corporation running cloud servers or video surveillance. The key differences are speed, reliability, and cost. Some technologies are perfect for light browsing, while others are built for high-demand environments like video streaming or enterprise operations. At home, we most commonly see technologies like DSL and older broadband technology that runs over phone lines or cable, which is very common in residential areas and provides high-speed internet through coaxial cables. Fiber to the home provides ultra-fast internet speeds and is expanding rapidly in urban and suburban areas. Cellular connections are used for mobile devices or even as a primary internet connection via hotspots or cellular routers. Satellite is useful in remote or rural areas where other options aren't available, but often comes with higher latency. Dial-up is a legacy technology that uses traditional phone lines. It's largely obsolete today due to extremely slow speeds and limited functionality. These home and SOHO solutions are designed for affordability and convenience, and except for dial-up, have enough bandwidth to support modern internet use, like streaming, video calls, and cloud access. Many SOHO users also take advantage of VPNs and Wi-Fi mesh systems to improve coverage and security. Businesses need more from their internet, higher speeds, better reliability, and technical support. While technologies like DSL and cable are still used, providers often offer enhanced business-class versions with better upload speeds, static IP addresses, and enhanced service-level agreements. Other common business connections include dedicated leased fiber, a high-performance private fiber connection that offers consistent speeds and bandwidth exclusively for one organization. Ethernet WAN provides Ethernet connectivity across a metropolitan or wide area network, ideal for connecting multiple business sites. Fiber to the building delivers fiber to a shared business structure, such as an office complex, with internal distribution to tenants. Legacy T1, T3 lines are older technologies still in use in some areas for their stability and guaranteed bandwidth. And satellite is sometimes used in areas where a better wired solution is not available. These services support large file transfers, remote access, voice over IP systems, and mission-critical applications, all with the reliability businesses need. At one time, voice, video, and computer data each traveled over separate networks. Telephones ran on their own circuit switch systems, video was delivered via coaxial cable, and computer data moved over dedicated data networks, whether through Ethernet in offices or dial-up connections at home. Today, everything runs over a single, converged IP network. That means one connection, like your home fiber line, can carry all your internet streaming and phone data. This convergence saves money, reduces infrastructure complexity, and makes networks easier to manage. In modern networks, all types of data, video, voice, and web traffic are transmitted as IP packets over the same infrastructure. This is the power of convergence, efficient, scalable, and smart networking that supports everything we do. When we talk about reliable networks, we're really talking about intentional design, building systems specifically to recover from failure, grow with demand, deliver performance, and stay secure. In today's world, we expect networks to just work. Whether we're making a call, streaming a video, or managing critical business data, reliability is key. Network architecture refers to the underlying technologies and design principles that support the infrastructure, the systems that move data efficiently and securely across the network. At the foundation of good network architecture are four key features: fault tolerance, scalability, quality of service, or QoS, and security. These concepts guide how we build and manage networks, whether it's a small office or a massive global network. Fault tolerance is all about keeping the network available, even when something goes wrong. Think of it like building multiple paths, backup devices, and failover systems in place to ensure that a single failure doesn't take the whole network down. This is called redundancy. For example, if a router fails, the network can reroute traffic through another path, or if a server crashes, a backup server takes over. Redundancy is critical for businesses that depend on 24/7 uptime. A scalable network can grow smoothly without major overhauls. As an organization adds more users, devices, or applications, the network should be able to handle the increased load without slowing down or becoming unstable. Good network design anticipates future growth with modular hardware, like switches or routers that let you add extra ports or modules as needed, scalable protocols, and flexible addressing plans. It's not just about size either. It's about growing smart. Not all network traffic is equal. QoS helps manage how data moves through the network, especially when bandwidth is limited. Certain applications, like video calls and voice traffic, are sensitive to delays. QoS gives them priority over less time-sensitive tasks, such as file uploads or background updates. Imagine you're on a Zoom call, uploading a file, and streaming music all at once. That's multiple data streams sharing the same connection. QoS makes sure high-priority traffic like voice and video gets through smoothly when it matters most. Even during peak usage, QoS keeps critical applications running smoothly and responsively. A reliable network also has to be a secure network. That means protecting both the infrastructure, the physical devices and systems that keep the network running, and the information flowing across it. Infrastructure security focuses on securing routers, switches, access points, and other hardware from physical threats or unauthorized access. Information security ensures the data on the network stays protected, guided by the CIA triad: confidentiality, keeping data private and accessible only to authorized users; integrity, making sure data isn't altered or tampered with; and availability, ensuring the data and services are accessible when needed. We use tools like firewalls, authentication systems, encryption, and access control to support these goals. Security also involves policies, defining who can access what, from where, and when. Without security, even the most fault-tolerant, scalable network can become a liability. Networks aren't static, they're always evolving, adapting to new technology, changing user habits, and growing demands. Every year, new devices, applications, and services push networks to become faster, more flexible, and more secure. Let's dive into some of the trends that are shaping networking today. Bring your own device, or BYOD, means that more people are using their own personal devices, like smartphones, tablets, and laptops, to connect to corporate or school networks. This offers convenience and flexibility for end users, but also creates challenges for network administrators. Networks must handle a variety of device types, operating systems, and security levels. This requires strong security policies, network access controls, and often the use of tools like mobile device management to keep networks safe and efficient. Online cloud-based collaboration tools like Cisco WebEx Teams and Google Workspace have become essential in today's workplace. They allow teams to chat, share files, edit documents simultaneously, and manage projects, all from different locations. This shift has changed how networks are used, increasing demand for reliable, low-latency connections, and putting more traffic on cloud-based services. Video communication took off during the COVID-19 pandemic, turning platforms like Zoom, WebEx, and Google Meet into household names. Video calls require more bandwidth and low latency compared to regular data, so networks have had to evolve to prioritize video traffic, using technologies like QoS. This shift isn't just a temporary response. Video is now a permanent and growing part of business and social communication. Cloud computing has transformed the way organizations build and use networks. Instead of hosting servers and applications on premises, many companies now use cloud providers like AWS, Azure, or Google Cloud. Modern networks must be designed to efficiently connect to these cloud services, sometimes combining local resources and cloud infrastructure in what's called a hybrid cloud. This means networks need to be fast, reliable, and secure to handle the dynamic flow of data. Smart technology, also known as the Internet of Things, IoT, is everywhere, from smart thermostats and lighting to connected security cameras and appliances. These devices often have unique networking needs. Many are small devices requiring minimal bandwidth, but always requiring reliable connections and strong security. Networks need to be scalable and flexible to handle this explosion of devices, while also protecting against the new security risks IoT can introduce. Powerline networking is a niche technology that uses existing electrical wiring to carry network signals. While it's less common than Wi-Fi or Ethernet, it's useful in situations where wireless signals are weak or when running Ethernet cables isn't feasible. It appears on the Module 1 to 3 exam, so be prepared. Wireless broadband technologies are rapidly expanding internet access, especially in areas where laying cables is difficult or costly. Fixed wireless broadband often relies on wireless internet service providers, or WISPs, which use radio antennas to deliver internet to underserved locations. 5G, in particular, promises higher speeds, lower latency, and support for massive numbers of connected devices. This trend is crucial for enabling smart cities, autonomous vehicles, and IoT on a large scale. The course currently ignores some trends that I think are worth mentioning. Fiber to the home delivers blazing fast, reliable internet directly to residences using fiber optic cables. It has become common in suburban areas and is even expanding into some rural communities. It supports today's bandwidth-heavy applications like streaming and gaming. Artificial intelligence, AI, is increasingly integrated into networks, not only to automate configuration, optimize traffic, and detect anomalies, but also to enhance IT help desks and assist network engineers in troubleshooting and managing complex systems. While AI and fiber to the home, along with emerging technologies such as quantum networking, aren't on the module exam, they're exciting technologies worth watching in this ever-evolving field. It feels like every week there's another major data breach in the news. Whether it's a company's sensitive data exposed or millions of user records leaked online, it's a reminder that network security is no longer optional. As networks grow more complex and connected, keeping them secure is one of the most important challenges we face. Let's take a closer look at the types of threats we face and the tools we use to defend against them. Threats come in two main forms: external and internal. External threats are what we usually think of first: hackers, malware, phishing emails, and ransomware. These attacks come from outside the organization, often probing for weaknesses like open ports or vulnerable systems. But internal threats can actually pose a greater risk. Why? Because internal users have already made it past your firewall. They're on the inside, with access to systems, data, and often trust. An internal threat might be a malicious insider, someone intentionally stealing data, but often it's unintentional. A user clicking on a phishing email, plugging in an infected USB drive, or misconfiguring a system. Because they bypass traditional perimeter defenses, internal threats demand a different and often more vigilant approach to security. For home users and small offices, security tends to focus on basic safeguards, anti-malware and antivirus software, basic firewall filtering on a home router, and a secure Wi-Fi password. These tools are usually enough to protect against most day-to-day threats in a small network. But in a business or enterprise environment where the risks and attack surface are much greater, the security stack gets deeper. Companies deploy next-generation firewalls that inspect and filter traffic more intelligently. They use VPNs to securely connect remote users. They implement intrusion prevention systems, IPS, to detect and stop active attacks in real time, and access control lists, ACLs, to tightly control who can access what and under which conditions. These systems work together in layers, because no single tool can defend against every kind of threat. Good network security is always intentional, layered, and adaptive. As we wrap up Module 1 of Introduction to Networks, let's take a moment to reflect on what we've covered and why it matters. We started by exploring how networks affect our everyday lives, from how we work and learn to how we connect with friends, stream entertainment, and access information. Networks are everywhere and essential to modern life. We looked at the components that make up a network: end devices, intermediary devices, and the media that connects them. We broke down host roles and saw the difference between client-server and peer-to-peer models. We learned how network diagrams help us visualize and plan using both physical and logical topologies, tools that are useful whether you're running cable or designing security policies. Then, we dove into the different types of networks, from home setups to enterprise systems, from LANs and WANs to the internet, intranets, and extranets, all built to serve different needs at different scales. We talked about how we connect to the internet through cable, fiber, DSL, and wireless, how all types of traffic, from video to voice, now run over converged networks. We also discussed how fault tolerance, scalability, QoS, and security make networks reliable. Next, we explored network trends like BYOD, IoT, cloud computing, fixed wireless, and AI, showing how the industry continues to evolve and where your career might lead. And finally, we tackled network security, understanding the difference between internal and external threats, and how networks are protected using everything from basic safeguards to enterprise-grade firewalls, VPNs, and intrusion prevention systems. So, what's next? In Module 2, we'll take all this theory and start applying it. We'll learn how to configure switches and end devices, access the Cisco IOS, and assign the IP settings that allow communication to happen. We'll also introduce basic command line interface navigation, build confidence with essential commands, and add some security features to lock things down. By the end of the next module, you won't just understand networks, you'll know how to build one. Let's get ready to bring our first small network to life. Make sure you click that subscribe button, and let's keep building your networking knowledge one step at a time.